Second. What you see in there is the PowerPoint. And as I said, the PowerPoint has been modified to include the session of today. And then I've added another folder with some code, some R code. And that folder is called Support Vector Machine, SVM. So you'll see that folder there. It's not a big folder, so shouldn't take you too long to download for today. And there are 2 files in there that we are going to use. So with having said this, let's begin. So I'm going to open the PowerPoint. As I said, I have modified some of the slides since we met yesterday. And yesterday we, let me go to the beginning of the support vector machines. So yesterday we did some theory. So we looked at what...
Yes.
You can't see the screen? Sorry? Somebody is saying they can't see the screen?
No,
right.
We can see the screen.
You can see the screen, okay. Right, so what I also did is I've added a link to the resources for the course on some of the slides, so that it makes it easier for you to find again the resources. So yesterday we talked about the support vector machines as being another example of supervised machine learning for classification. And I'm not going to go through this again, but what we said is that sometimes the data that we are looking at is not linearly separable. So we won't be able to apply, for example, linear regression techniques on our data because of the kind of data that we have. So in this image, as an illustration, you see 2 groups of data, or data that belongs to 2 groups. So you have the circles and the triangles, and they are plotted on a 2D plane. So it's not easy to see how you're going to separate this data. So what support vector machines do, they use what's called a kernel trick. And this kernel trick is a mathematical function that's applied on your data to move it on a higher scale. And the idea would be when the data is moved on a higher scale, that you'll be able to separate the data in there. And I've added a little bit of more information on these slides. So the idea behind support vector machines is that as you are transforming your data into this higher dimension, your data can become linearly separable. So if you have, n predictor variables, an n-dimensional space, then a hyperplane or an optimal hyperplane is called a linear decision surface. So you're looking for this decision surface. So for an n dimensions, it will have n-1 dimensions. So for example, for 2 variables, the surface is a line. So that's the typical regression line. If you have 3 variables, then you're looking for a plane as being something that separates your data. So that's what we said last time. So the algorithm is pretty much similar to what we saw with the typical supervised learning. So we have an input. Again, it's a labeled input. And we pass that to the support vector machines. What the support vector machine does, it transforms this data using the kernels into this higher dimension where it can linearly, or it can separate the data using a plane, a hyperplane. Okay, so what I wanted to do today is to show you some examples. In R, there are two packages that allows you to work with support vector machines. Sorry, I have a typo there. So it's KernLab and E1071. So the first one is more powerful, but the other one is easier to use. And in the second library, we have this SVM function, and you're going to see it. And this SVM function is the one that is taking in your data, or your training data set, and it applies some transformations to that data before it is fit by the model. So let's have a look at the R example. So what I'm going to do is, let me stop sharing on this screen. And I'm going to share this screen here. Okay, so in the document, in the folder I shared with you, there are two files. One is called visualize kernels, and the other one is called R classification. So I want you to look at the first one that I mentioned, which helps us visualize the kernels. I don't suggest that we run it myself, because I've run it already, but you should run it on your machine. It could be that you'll have to install some of these packages. So here, you'll have to install the support vector machine package, and the other one is for graphics, for 3D graphics. And you install the packages in the usual way with the install packages command on the command line. So what you see here is that this simulated some data, and the data was not linearly separable in a kind of a 2D plane. It had a lot of dimensions, and the support vector machine models, which you see being created here using the SVM function, will take in the data the data points, and will apply a kernel to the data, and allows you to separate the data on this higher plane. So that's just a nice visualization I thought I could share with you before looking at how to apply SVMs. Okay, so let's go to the example that I prepared for you. So this is an example I borrowed from a book. You see the source there. If you are able to obtain the book, that's quite a good book to read. So we are going to use this example for today. There's a new data set that's being used. So in this case, this data set comes from the UCI archive, the data archive. So if you have never used it before, there are a lot of data sets on this archive that you can explore. The data set that is being used here is about breast cancer. So maybe we should review that data, if you like. Let me just open the website for you. Just give me 1 second. You can open the website on your machine just to see what information we are given about this particular data set. Okay, 1 minute. I should share my screen. Just give me 1 second. Once I have this ready for you. Okay, so let me share the whole screen. Just give me 1 second. Okay, so you'll see that I am here on the UCI website, and there are several data sets. They are all cataloged according to the subject, data type, keywords, and so on. So the one that we are using, let's look again what we are using. So we are using the breast cancer data. I'm thinking that is the diagnosis data. Let's have a look. And 9 features, 30 features. Let's have a look how many features these ones have. So the data, I already brought the data into this document. Give me 1 second to look for it. Where is my data? Okay. I don't, oh yeah, DS. Right, so 11, 9, 1 minute. Let's see. Yeah. Okay, so we have our data and it's in the variable breast. Okay, great. So if we look at our variable breast, you can see that there are 11 variables here that are being given. So this means that actually it's not the diagnosis, but probably the other data set. Let me look again and see. 9 features. So I'm thinking that is this one here, the original data set. And we can look at what the variables mean. We can see that I have some codes, sample code number, like an ID, and then some features about the presentation of the lump or that is being tested to see whether it's malign or benign. So there is a clump thickness, something about the uniformity of cell size, uniformity of cell shape. So these are all observations. And you can see they are integer observations, marginal adhesion and bare nuclei and so on. So, you know, you can see here that there are quite a number of characteristics. I'm not a medical professional, but this would probably make a lot of sense to somebody who works in that field. So I have my data set, and the idea would be that you would want to diagnose whether some tumor that is being observed is malign or benign based on this data that you see here. Okay, there are 11 variables because this one also includes the class. So if you look at this data set here, we are given the 9 predictive variables. But in our R data frame, we also have the class. And we are given the class of, so the categorization of whether the tumor is malign or benign. The next line of code is simply extracting the names of the features that you are looking at. So you will see it in here, the names, if I can see that, but I think those are just in here somewhere. Okay. Oh, I think that one is just an internal variable. So the names of the breast, oh yeah, you assign them, right? You assign the names of the variables because they probably come with different names that might contain some symbols, right? I didn't actually see what they were, but you can run this and check. So what's happening here is you are assigning some names that you can recognize. So ID, you're renaming the first variable with ID, and I think it's removing these underscores probably as they come from the data set. So you are renaming the columns to make it easier for you to work with. You are also looking at the class. So you're extracting the labels that you want to apply from the data set. And that's the last column. This is the last column that you're looking for. And here you might want to omit values that are NAs. So you are taking them out. And the remaining code is preparing your data set for training. So you are extracting the train and the test from your data. And you can see here that there's a sample. So a sample is being created here and it's 30/70. Okay. So that's how, in the proportion 30/70, that's given there. So let's run some of this now. I think I've run this before, but for illustration, I'm just going to run everything. So I'm building my data. Okay, I'm setting the seed. If you remember, this seed was for replicability, so that every time you run this notebook, you get the same results, and you're creating your train and your test. And right, you will see what's the content of the train and the test sets, how many you have in each. So in the training data set, you have 302 observations that are benign, 176 that are malign. And there are 478 observations in the train and 205 in the test. So they were split in the proportion that you saw, which was 30/70. Okay, so now that you have the data ready for training your model, for comparison purposes, we run a logistic regression now. So before running a support vector machine model. So this will now try to fit the data that you have using logistic regression. And you are predicting the class based on all the variables. And there were 9. Okay. You can look at the accuracy to see what's the accuracy of your logistic regression. So this gives you information about the significance of each of these variables and how they contribute to your data, to your class, to predicting the class, basically. And some of these variables you can probably ignore, looking at the errors, right? So the ones that you would keep that are more significant are starred. You can see that they have 3 stars, 2 stars, and so on. So some of the other variables you can probably safely ignore because they don't contribute to anything with respect to this logistic regression. And let's try to run this model to predict on the test data set. Oops, where am I? Yeah. And look at the performance. So you can see here that the model was able to, this is the confusion matrix, if you remember, where we have, let me just clear the screen. Oh, well, you can look at the bottom of the screen. Hopefully you can see. You can see what were the false positives, right? And what were the false negatives, right? So there were two false predicted, 3. No, wait a minute. So you have predicted benign. Yeah, so there were basically 3 false positives. So in 3 instances, the model predicted that the tumor is benign, but actually the tumor was malign with respect to this data set. There's another little code there that gives you the stepwise regression, but I'm going to skip that. I don't think it's necessary for our illustration, but I wanted to share with this notebook with you as it was, but you can run that. Remember that we looked at decision trees, so we can also try to run a model that uses decision trees. And this is using the library that we've used previously in the notes. So let's run this. And we can plot the tree. They did not plot the tree. I don't see it plotted the tree. Let me go back. I have run the tree before. 1 minute. This is the tree that is being built. And you can see which are the features that were chosen to build the tree. Now, if you remember about these trees, is that these trees can grow in height and in complexity when there are many predictive variables. And in many cases, there's more than one tree that you can build. And in many cases, there is a cutoff point. So there is a level beyond which the trade-off between the complexity of the tree and the predictive power of the tree is weaker. So this is where you cut the tree. And you do that by analyzing the errors. And you are looking, so you see this dashed line is already done for you. So this dashed line means that you should really look at the complexity that's about that level or below. So there's no point of you growing the tree because you're not going to improve in terms of the error. So in this example, you can see that this level is chosen here, level 3. So the complexity parameter is 0.17. So by analyzing the errors, just like we looked at in the previous session yesterday, you can build a pruned tree. And I think this is the one that I showed you, I visualized. So let me run the prune tree. Sorry, I'm running. Let me just clear this because there's too much baggage. So after I created my tree, I analyze the error. So this is the error that I'm looking at. And I choose the complexity parameter that I want. And I'm going to prune the tree below that level. Oops, I'm still running in the wrong window. Let me go back here. Okay, and there's another library that I want to show you, and this prints decision trees nicely. So it has this fancy way of printing decision trees. So I have already installed it. So I'm just going to use it, and you see the tree that is being created for this scenario. So we talked about how these trees are being built and how the features are chosen to help you split the training data set. So you see in the root node, I have all my training data. So 100% of my training data is in that node. And that training data is split in two, yeah, in malign and benign, right? In that proportion that is shown in there, 63 and 37%. Okay, so this is our tree, and you can print, you can look now at the prediction of the tree and how good it is. And you'll be able to compare this with the predictive power of the logistic regression we had before. I've deleted it, but if you remember that actually what's changed is that the false positive remains the same, but you see here you have the false negatives that increase. So tumors that are actually benign are being classified as malign. Okay, so this is the decision tree, that the type of decision trees we spoke about before. There is another type of decision tree. We didn't do this in our session, but if you want to have a look at what is called conditional inference trees, then you can do that with the example that's given here. I'm going to skip this, but if you want to run this, you can, and have a look at the conditional inference trees that can be built. So let's have a look now at random forests. So if you remember yesterday, we looked at random forests and we said that there is sorry for the typo. There are some problems with decision trees. The first problem is that it's difficult to build a whole tree that fits the data well. And if you do build a very large tree that fits the data, you can also, the more features you use, the more likelihood there is that the tree will overfit the data. So it will not be a good predictor for new values that you're going to see. We also said that these are sensitive, these trees, the way you build the trees are sensitive to the sample that's being used to build the trees. So if you have changes in the data, that's going to affect these trees that are being built. So one option was to do what we call bagging. So we could generate lots of trees, but they are smaller. For each tree, we only consider a small subset of the features. So we build lots of these small trees that represent aspects of your data, and then you kind of combine them. They fit the data, and then you combine them. So then we talked about two ways of combining the trees, using ensembles, for example. So this is where the use of random forest comes in. So the random forest is, if you look at the notes, is a collection of trees that are independent of each other. So they're not correlated. And it allows you to build a better fit of your data than to rely on one tree, because you build several that are simpler, and then they give you a good estimator of your data. So you can use this library called Random Forest. I'm going to run this. Again, you set, oh, maybe I have to run it now, okay? Set the seed again and feed. I'm not sure where this install packages keeps coming for me. Let me just clear this, okay? And this, you know, this function here, it builds your forest for you. So you're not actually controlling how many trees are being built. You're simply allowing the algorithm to do that work for you. Okay, so let's fit the forest, and we can see here what the confusion matrix is in terms of the results that the random forest would have on our data. So we can see that both the false, compared to the logistic regression, both the false positives and the false negatives increase. And let's fit the data. Actually, we did that, fit the data on our class. And you can see a little bit of information about the importance of each feature for the split that was made in the random forest. And let's look at the predictive power. And we can see here that the predictive power of our forest, of our random forest, I think is slightly better, right, than what we saw before. So, okay, and now this takes us to support vector machines. So support vector machines, they have their own library. As I said, I mentioned two libraries that you can use. This is simpler to use. So we're going to use this library. Again, you set the seed for running your algorithms, and then you call the support vector machines algorithm. Just to say here that this support vector machine transforms your data, so scales each variable you have so that they have a mean of 0 and standard deviation of 1. So all your numerical variables will be scaled that way. Okay, so let's run this and fit. And you have some information about how many support vectors were used. The other thing you see here that the kernel function that is being used is what's called the radial basis function. So in your notes, I put a comment about this. So by default, the kernel that is being used is the radial basis function. And this has two parameters. One is called gamma and the other one is called cost. And these two parameters is what you can tune. So you can fine tune them to train the support vector machine. So if you can see in the next example, you are tuning the support vector machine that has been created by adjusting this gamma and the cost. And in the notes, I mentioned there that gamma controls the shape of the hyperplane that separates your data. If you have a larger value of gamma, then you have a larger number of support vectors. Sorry. And by default, gamma is set to 1 over the number of predictors. So if you have 9 predictors, that will be 1 over 9. And the cost by default is set to 1. So what this formula is doing now is basically picking values for gamma in the range that is given there. So 10 to the power minus 6 up to 10. So values for gamma in that range are being selected. The same for the cost. So the algorithm will create lots of support vectors as is ranging through these values for gamma and the cost. And several models are being created. And out of these models, you choose, or the one with the fewest, 10-fold cross-validation error, in the training sample is chosen. So that's the idea. So let's run tuned. Did we set the seed? I think we did, yeah. And let's print it. It's still working, it's still thinking. I see there are some questions in the chat. Let me go to the chat while this one is doing a bit of work. 1 minute. Oh, right. I think I missed that one. Finish downloading. Share the tools to analyze the database of diagnosis of different cases. How to get the diagram. Okay, so let me then address some of the questions in the chat. There's a question about, hopefully you've managed to download the code by now. Is anyone who hasn't managed to download the code for today? So it's in the folder on Google Drive. I think the folder was shared already. Right, and you are able to find the files in there, hopefully. I can see Joel, he shared the folder. There was a question about the diagram. I'm not sure what that referred to. Was that the 3D image that I was showing? Yeah, so the 3D that I was showing was generated using this code, this visualize.r code. And this is something I gave you to run in the folder. But we can run it at the end. If people want to do that, we can run it together. It should be fairly easy to run without much modification. Okay, so our model has finished tuning, and you can see that the result of the tuning was new values for the gamma and the cost. So these are the best parameters to be used for this model, and the best performance, we have it in there. So let's try to fit the data. So now I'm going to, okay, so since I have the best gamma and the best cost, I can rerun the support vector machine, or I can create the model that has these parameters, because what I was doing before is I was looking for this model. I was looking for the model that gives me the best fit. So let's run again the seed and the fit and the predictive and the prediction of the model on the test data here. And let's print the performance. So we have our confusion matrix showing us the number of false positives. So these are smaller than what we've seen before. And, but I mean, all these models are kind of similar. They're close to each other in terms of performance. One thing to say here is that the support vector machines are said to be preferred to be used when you have more features than actual data points. So if you can look here, you know, our data set is quite small. I mean, we don't have a lot of data points. I mean, the number of features is not larger, but I mean, also the number of observations that we have available is quite small. There is a nice piece of code that comes next, and this code prints basically the performance of the models that we saw before in a nice way, so you can analyze them. So this code, I'm going to just run, and I'm going to print the performance of each of the models. So you can see a table basically from which I'm extracting all these measures of accuracy. So sensitivity, specificity, the predictive value, the positive predictive value, the negative predictive value, and so on. And you can see that there's not a lot of difference in terms of accuracy, but again, it depends on the kind of errors that we are willing to live with. That will dictate which model we are going to choose. Okay, so let me go back to our PowerPoint. Or maybe I should give people some time to run this. How are people getting on running this file? Maybe people can say something. Are people able to run this code? Are there any issues? Okay, good. Right. So let me give, is it helpful if I give people 5 minutes to just run the code and catch up or come to the same point where I am? Would that be helpful? Okay, so Martin, you have an error. Right, would you be able to write in the chat what the error is? Just make sure you have all the data available. D3 pruned not found. Okay, so that means that you might need to import all the libraries. Did you try to import all the libraries? D3 pruned not found.
Yes,
Okay.
I did. I imported,
Did
but
you
then
run-
I'm getting.
Did you run this line, number 60?
Yes, I did, and I got an error actually from around that point.
Well, what I can advise that you do is you can try to run the lines again together, for example. Yeah.
Okay.
So you can highlight the region all together rather than one by one, just in case, you missed a line.
Okay, let me do that and see.
Yeah. Did that work, Martin?
Still trying. I realized I think I erroneously deleted some of them, so I'm just getting it back.
Okay. Yeah, so maybe also just as a tip, you don't have to run things line by line. You can also highlight group of code together and run them together so that you don't miss any of the required executions.
Okay.
So what you could do is you can highlight this whole thing, the data aspect. So creating up to this point, loading your data and creating the train and the test, and then making sure that you have those no errors and the data is in the data tab here in the environment. Okay. So let me now switch to the presentation again. Right. I'm going to share this with you. So we covered some packages in R. Sorry for the typo there. As I said, there's a typo in the KernLab library. The packages that exist in R for support vector machines. We used the second one, and the reason was that it's easier to use than the KernLab library, but KernLab is more powerful. And inside that package, we use this support vector machine function. So what the support vector machine function did was to, one, in the background, basically, it would scale the variables, each variable to a mean of 0 and standard deviation of 1 before fitting, and then it will apply a kernel function. So we said that by default, the kernel function that's used is the radial basis function, and this is a nonlinear, this function achieves a nonlinear mapping. So it can handle both linear and nonlinear relationships between variables and predictors. Just a note there that support vector machine cannot deal with missing predictor values very well. Not as well as the support vector machine can. But if you remember, we actually removed the NAs. There was a line there where we omitted the records that were incomplete. And with the support vector machine function, what it would do is it will help us find the best gamma. So it has two variables to control, the hyperplane that separates the data. One is called gamma and one is called the cost. So it will create these models by ranging over values for gamma, values for the cost, and then it will choose the best model. And it will give you the gamma and the cost that can achieve that best model. Okay, and we looked at a bit of code. So this is the code that was achieving that. Right, so we have the support vector machine defined, we tuned it, and then we chose the best predictor. But there is a problem with both random forests and support vector machines. And the issue is they are like a black box. So they are black box predictions. And the reason is that we're not very easily able to explain the link between all those trees when it comes to random forests, for example, all those trees that are being created, and what do they mean, and how do they achieve that best fit? And the same for support vector machines. We have all these support vector models, but how do each of them relate to the data that we are trying to predict? So we say that these are black box predictions. And when it comes to black box predictions, the problem is that, well, we need to be able to explain how we arrive at a decision, because classification models can have serious implications in people's lives. And, when it comes to issues of mental health, right? This could trigger some potentially serious situations when people are misclassified. And this can be, misclassification either way, like either the false positives, right? Or the false negatives. And I just put an example here. I think we talked about this in both of the two previous sessions we had. So, when you have, let's say, conditions that are quite rare, right? I mean, okay, maybe these numbers that are on these slides are not accurate, but let's say schizophrenia is quite rare, and the prevalence is, let's say, roughly 1% in the general population. So of course, 99% of the time, I mean, the biggest class is the people who are normal, right? They are non-schizophrenic. So so basically you can randomly, you know, your random guess can be quite good. Most of the time it will be correct, right? But if you build a classifier, yeah, it's not going to be that good if your classifier can't do better than a random guess. And we looked at some measures, right, that were trying to ascertain the accuracy of a model versus, you know, on top of a, or in comparison to a random guess, right? So it's not a good thing to have a classifier that misses out, you know, schizophrenic people. So, right, because those can be dangerous. I don't know what the situation would be. But similarly, you also don't want to diagnose people wrongly. So, you know, what if the features that you're using, I mean, you know, when it comes to something like this, it's not just a matter of data collection, but it's also a matter of data representation, right? Because remember, what you'll be doing is that you'll be using some kind of clinical questionnaire or clinical diagnosis protocol or flow to diagnose a condition. And then once you have all this data to really use a machine learning classifier, yeah, you have to encode this data numerically. So there is always a loss of information, and there's always a danger of encoding being wrong. Okay, so you would want to be able to explain. You would, if you remember, there were two principles that should guide our AI research and our AI models, and those were responsible AI and explainable AI. So I wanted to talk to you about this explainable AI. And there are movements or frameworks that have been developed, and I've added a link there that you can look. And in R, we also have two libraries that allows us to explain or try to explain what's happening behind these black box models. So here we have an example of a patient. So we just created a patient called Alex, and this is a new patient. So we put all this data. So we have 9 features, right, into a data frame, and we put that into a variable called Alex. So this Alex has value 6 for clamp thickness, size uniformity is 1, shape uniformity is 1, and so on. And we have our model already trained. So here we can use the random forest model. So we take our random forest model and we predict what's the outcome for Alex. And let's see what the model tells us. So let's run. Let me just do a new share. Just give me 1 second. So we are back in R, and you're going to see 1 minute. Further down here, you're going to see our use of the library called DALEX. So this is one of the libraries in R that allows you to do explainable AI on your model. So you have our library. You might have to install it. So just run install packages for DALEX. And here we have our person. And let's run this. Oh, object A not found because I've highlighted it. Sorry for this. And let me run Alex. So I have Alex here in my environment, and I'm going to predict the class. So you can see here that I have a prediction, and this is given in terms of probability. So I am told that there is a higher chance that the tumor that Alex has is malign. So 65.8 probability that is malign and 34.2 probability that is benign. Do I trust this right? Do I trust these results or not? So let's run this explainer. So to do that, I still have to, again, set my randomness so that I can replicate these results. And I run an explainer function, and then I plot. Okay, so what do I see here? I see two things. Well, one, in the console, you see the actual values that tells you how each of the features contribute to that result that you saw there. So the prediction that we have, which is 65.8%, right? 65.8%, that is the tumor is malign. And in the plots window on the right, you see a graph that visualizes the contribution that each feature brings. So you can see that from bare nuclei, there is a big contribution. Also from the epithelial cell size. No, wait a minute. Clamp thickness has value 6, bland chromatin. So you can see some of those contributions that come from those variables. Now, if you are his doctor or somebody who understands the case, then you might want to check this, have maybe redo tests. I don't know what could be done to make sure that the result is accurate. I mean, there was a high-profile case in the UK. Maybe this is just a big parenthesis here, but it's a high-profile case in the UK that happened not long ago, and a certain doctor had needlessly operated on females, breast cancer patients unnecessarily. They were proven not to have had any tumor that was cancerous, but they had to. They basically did undergo surgery, and it was all driven by, I don't know, madness, greed, money. I don't know what you want to call it, but these results, if you rely on a machine learning model, then remember that framework we had before, who takes control? Is it the model? Is it the doctor? And also, what happens when things go wrong? Can you check them? And this is where this explainable AI comes in to help us understand. So this is one of the libraries that's available. And the other one that I included in here that you can use as an example is a library called Shapely. So this library called Shapely also allows you to do something similar. So let's run this code and plot it. And you can see now the contribution that these variables have to the final score. Okay, so this 9, okay, there's a question. What do those values mean? Well, if you look at the actual values for the patient that we had, so those are the values that the observations, basically, the values for the variables for that patient. So this patient had value 9 for bare nuclei and so on. And the actual bars on the chart gives you the contribution. Yeah. So let's have a look a little bit here. So you can see that in the numbers here, you have the bare nuclei, which had the value of 9. Has a contribution to the score, and it gives you the minimum value and the mean, the median, the mean, value for that particular variable. So it's a range. Of course, these are not precise, right? It's not 100% precise, but it gives you an idea of which one is important or the most important. Basically, which variable drives the prediction and to what extent it drives the prediction, and whether it's a positive or a negative to your prediction. Now, I think you'll need to be the health range for each number. Yeah, I agree with you. I think, this is just an example that shows you how things work, right? But you need to be able to interpret them and read them. And I'm not an expert, right? But you are right. I think it would be useful to know what are the ranges for these values that they should go into. Is 9 a big number, in that range? Is it average, and so on? There's a hand up.
Yes, I'm not clear regarding maybe the numbers. As you said, it's not abbreviation. But what if we were not to include more patients, for example, 5, 6 patients? Do we have to put the number of observations for each person, or can we maybe make it run it automatically?
Okay, so these are not number of observations. These are actual values for something that's been measured. So maybe the tumor has been looked at the microscope. I mean, as I said, I'm not X-ray. I don't know. So these are readings. So this bare nuclei, it's a reading of 9. So what you are trying to do is you have a model already that you trained. So remember what we did is we took a data set, right, from the UCI. So that data set contained data points or observations about a number of patients along 9 variables. So these are the 9 variables that you see here: clamp thickness and so on. So for all those patients, they had measurements being done, I don't know, in a clinical setting. You will have to look and see how this data was actually collected, right? But you have data collected about these patients, and an expert had already given a diagnosis for these people. So we know that we know what class each data point belongs to in that data set that we took from UCI. Yeah. So what we did with that data set is to train these models that you see here. So we trained a forest, we trained a support vector machine, we trained a logistic regression model. So this is now a mathematical function that best fits that training data that we gave. The question is now the value of that model. So the value of the model is given by how well it can predict unseen data, something that, a new patient. So is it able to correctly classify or predict the class for that new patient? Does that make sense? Is this helpful, Matthias?
Yeah, thank you.
And in this case, we just created a patient. So this patient comes to the doctor and he is put through a series of observations. And for those observations, we have some values. Now, I don't actually know what 6 is. And good point there, Nifata, Andrew put in the chat, that it would be helpful to know, right? I mean, maybe the closest example that I can think of is, nowadays when you go to the doctor, they don't want to look at you very much. They just send you for a blood test, right? So you come back with your white cells levels and I don't know what's there, full blood count results. So you remember they list, if you have a look at them, it lists the ranges. So I actually don't know what 6 is, on what scale, is it average and so on. But it does look that is some kind of important number.
Sorry, I mean here, I wanted to know maybe if we include more patients, maybe 100,000 of patients, maybe you have to put this kind of number, or maybe how we can run. That's actually the question.
If you include more patients in the training set.
For example, like for Alex, maybe if we do have many cases, and for the same kind of things, maybe how we can maybe include in the model in this way.
Okay, are you saying that if you were to run, if you are to change these numbers, is that what you're asking?
Sorry, this number, for example, 6-1, everything is for Alex, yeah? Maybe I think this is for
Yes.
single case.
Single case.
Yeah, what if we wanted to include maybe more cases, maybe thousands of cases?
Yeah, you'll be running that in a loop. So if you
That's
are
what I wanted to know. Yeah, thank you.
That's right. You just run it in a loop. So you'll have, I mean, maybe here, you'll have to just create patient 1, patient 2, an array of Alexes, right? And then with the for loop, you'll be running the prediction model. So you'll have a for loop and you'll be running this predict on your patients, P1, P2, whatever you have. Yeah, sure.
Yeah, thank you. Got it.
Okay, so sorry for that. Okay, so this kind of concludes our session on support vector machines, and we had a quick look at this idea of explainable AI and what libraries people are working on to try to explain the meaning of what the models are bringing us. So I don't know if there are any questions. What we could do is break for 5 minutes for a healthy break and then resume. Joel?
Yes, I believe we can break for 5 minutes. So it's 15:20. We'll be back.
Okay, break for 5 minutes and we will. Thank you. Okay, so welcome back, everyone. I think we should start our second session. I'm going to share my screen again. And let's go to our PowerPoint. So we finished our first half today by looking at two libraries that allows us to do what we call explainable AI. So we looked at breakdown plots. So the breakdown plots allows you to see what contributes to the prediction that you see. So there are some explanations there. So in the slides, on the slides, so you can see at the top where you have the intercept. So the intercept is the predictive response value across all observations. So what's the probability that something is malign across all the cases? And then it's trying to explain how each variable contributes to those scores, or how they explain it, basically. So the contribution from bare nuclei would be calculated at that score, and so on. So I think this is something I can let you read and delve in so you can understand. It's not easy. I mean, these are really hard things. I mean, you have to really read it, think about it. It's not so easy when somebody just tells you numbers. But hopefully the code that I gave you allows you to do that, allows you to look inside this example and the data that was given. And by the way, these libraries you can apply to the other examples we had before. So remember, we looked at spam emails, and we also looked at weight and height. So you can actually apply these for all models that we saw before. They don't just apply to random forests or support vector machines. We also looked at this Shapley library. So these are additive explanations as opposed to the breakdown. And this helps you, right? Because you can just say how much comes from bare nuclei plus how much comes from bland chromatin and so on. If you want to read more, there's quite a lot of resources. So as I said, I'm not an R expert, but now I want to be, because I'm really excited to see, this beautiful library. So I have always tended to look to Python for my work, but really I enjoyed doing some R for this course. And there are many good resources out there to help you. And I've added some books. And as I said, if you want some resources and I have them, I'm happy to share and collaborate with you if you like. So please email me and contact me and be in touch. So this concludes our supervised machine learning. We've done quite a lot. Let me just take you to the beginning. I agree that we haven't looked at this in full details, but I hope that the resources that I put together for you are helpful. I tried my best to present things in a way that makes sense to me, and hopefully this can help you. So we started with types of AI, and we looked at two frameworks. that are applying to when people use AI. So those were responsible AI and explainable AI. We looked at one type of AI, and this is machine learning. And if you remember when we looked at the Turing code, right, there are several properties or several types of AI that one needs to consider. So if you remember, a machine that passes the AI test or the Turing AI test has to have several things. Two of them are linked to knowledge, right? So it has to have knowledge representation. It has to be able to represent the knowledge about the real world in a way that can be computable. It has to have automated reasoning. So there has to be an element by which the machine reasons about the information that's being given. Now, for machine learning, that reasoning is given by this machine learning algorithm that's giving us some kind of outcome, whether that's classification or prediction. So knowledge representation, automated reasoning, natural language processing. So natural language processing is all about being able to communicate with the machine. And I come back to this point in a minute. And then the fourth one was machine learning. So we looked at machine learning as a mechanism by which the machine is able to learn to absorb new data. So in the example we had before, when we see Alex, we can learn something about Alex because we have a mechanism by which we can fit Alex's profile in our model. So we looked at supervised machine learning. We looked at the model itself, relying on that training data set. We also looked at accuracy and performance and the meaning of these false positives, which are important. And then we looked at two examples. One was the spam filter example, and one was the weights example. Sorry, that's missing from the table of contents. So we looked at two examples and some challenges with the supervised algorithms. Then we looked at how to build, because there are many different types of machine learning algorithms. So we looked at two of the most important ones, I would say, and those are decision and regression trees. And I tried to show you how these decision trees are built. And hopefully through the examples that we did in the sessions, these decision trees now make sense. I would like to hear some feedback from you, whether you found the examples useful and whether these decision and regression trees make more sense, whether what we did helped you. Okay, and then we looked at how to measure and evaluate these decision and regression trees. And then today, we revisited support vector machines. So we said, okay, we can have different types of data. Most of the time, our data is nonlinear. We have many dimensions. It's not easy to fit this data with linear models. So we have these support vector machines. They use a trick, basically, to help us approximate or find a decision. So now, as our last topic, we want to go back to that component of natural language and generative AI. And before I start, why do we want natural language processing? And I would attempt to answer this, but basically because we want the machines to be able to understand our world. So remember what we said before, that encoding and knowledge representation is one of the biggest challenges in I would say computer science, but okay, machine learning. Why? Because when we solve a problem that belongs to the real world. It's a problem in the real world. And we try to solve that with the machine. but we have to abstract, we have to simplify. You know, the machine cannot look at the real world the way we do as humans, is not able to absorb all of that. It needs to be given the knowledge, encoded in some way. So for a machine to really get close to what we call AI, and remember we talked about narrow and supra AI, for example. Well, for that, the machine has to be able to understand a language, and it has to be able to see. So it has to have this computer vision, right, component. And these are hard things. So let's go into a discussion about this generative AI. And what I'm going to do is I'm going to tell you about the project that I've been involved in and what I've learned from that project. So let's go to the section. I should have put some links, right, to take me to those sessions faster, but let's go to that session in the old-fashioned way. Brute force, right? Brute force. Okay, so natural language processing and generative AI. So first, I'm just going to talk about generative AI, but NLP, or natural language processing, refers to a lot of different algorithms that helps us process text and speech. So this generative AI that we saw for text, because there's generative AI for images. These are a type of natural language processing, and we call them models, and they represent language and knowledge. And they have algorithms that are based on machine learning. And let me make another point here. Remember when I said there are two types of AI? So you have AI that's, or machine learning, it's one of them, right? You have two types of AI. One is based on logic. So you can represent how we deduct, how do we infer facts from knowledge. And machine learning is basically statistical, right? It's one type, so it doesn't have that logic component to it, but you can have natural language processing with logic embedded in it, not machine learning. But generative AI relies on this concept of machine learning. And the machine learning algorithm it relies on are trained on massive amount of text. And if you think of ChatGPT, we don't know actually what's been used for training ChatGPT. I mean, the whole of the internet, I don't know, massive amounts of text, academic papers, books. And just to make a parenthesis here, you know, the first models were trained on, you know, maybe Wikipedia or internet content, and they weren't very good because that, you know, these sources are, well, are not curated. They are not checked as much as books might be and academic papers and so on. So anyway, machine learning, so models for language representation. So they represent language in some way, vector, numbers, and so on. They use machine learning, and these machine learning models are trained on massive amounts of text. And they are able to answer questions in natural language. So you can converse with them. They can do complex tasks like extracting information, summarizing. So pretty impressive tasks, which we associate with human intelligence. And one thing that I didn't add here is they seem to be, so these generative models, they seem to be kind of accessible, right? Because they give us these APIs, or they give us these ways in which we can build our own model on top of them quite easily, or easier than you might think. So there are some examples of generative AI for text. So we have ChatGPT, and I think people are familiar with that. And this is trained on multiple types of documents, all sorts of documents. The task it can do, answer questions, summarize text, look up definitions, extract information. I think there's something missing there, find programming, a code for you, and so on. Then we have more specialized large language models, like MedPalm from Google. This is now trained on medical text and code data sets. So it can do more specialized tasks that are oriented to medical type of text. It can answer questions about medical text. It can interpret images. So, you know, maybe X-rays or something like that. It can generate reports, radiology reports. It can also access genomic databases to give you names of whatever genomic variants and so on. So it's a more specialized language model. Then we have this example here, BioGPT from John Snow Labs. It's trained on medical, scientific paper and clinical data. Again, it can do kind of similar stuff as MedPalm, generate clinical reports, summarize medical literature, answer medical questions, and so on. Again, another one from Google AI Labs, Clinical BERT. So this is now trained on medical text, including electronic health records and clinical notes. I don't know where they come from, don't ask me, but this is, again, a different, using maybe some more sensitive data. So you can say electronic health records and clinical notes are more sensitive in nature than something like an academic paper. And then I hope people don't think I'm being obnoxious here, but I've added the tool that I've been involved in, basically. So we developed a tool based on using large language models to answer questions on disease surveillance for community health workers in Malawi. So our tool was built on GPT models, and we specialized that model to answer questions that were specific to disease surveillance and forms that were used in Malawi. That's what we did in my project. So how do these, what technologies do these large language models use or leverage? And I'm listing the four main ones. So you have training. So they're able to create massive databases of knowledge that are chunked and ready to be processed by a computer program. So, and then used to train that model. Just give me 1 second, 1 minute. Sorry for that. Yeah, so they use training, similar training as you've seen for the supervised learning we talked about. And then they use these special algorithms that we call transformers. And these transformers are able to search and reconstruct text. So put the text together for you so that you can see it in, you know, a sentence that makes sense, right? The other technique that is used is what's called fine tuning. So this refers to directing the attention of these large language models to specific information or documents, so that particular document or type of knowledge or paragraph is used when answering. So it's basically directing the attention of this LLM to that specific information. And the other technique that's used is called prompting. So this prompting refers to techniques for querying, basically. So how to ask a question, what instruction you're giving to this large language model in order for it to construct an answer. So you can give instructions like create a table, do a summary, or, all sorts of instructions. So that is what's called prompting. So these are the 4 key techniques that are used for large language models. So if you want to build an application that leverages some of these language models, that you might encounter all of this, or at least most of this that you see on the slide. Okay, oops. So our tool, as I said to you, is called InterServe, and I will show you a little bit how it works. I mean, it's still under development, but these are the things that we had to put into this tool. I know that this takes us to a slightly different level, but the application has the front end, so you'll have to have some kind of UI or interface, and you'll need to have a database. So you see here that we have a database on the Amazon web server. So we have this database where we put our knowledge. And we use a language model that exists. So that language model that exists can be OpenAI, for example, GPT-4. So the way the application would go is something like this. The user enters a question on the interface, just like you do in ChatGPT. This interface is handled by some backend. So you have some mechanism of taking this question and do something with it. So what can you do with it? Well, you can send it straight to OpenAI to return some answer or embedding. We call some of these things embeddings. And or you can also look at the type of question that's being asked and generate some prompts. So you can see here, you have, well, this user is asking about, let's say, symptoms. Then you might want to send an instruction to the large language model to generate some kind of answer that is looking for symptoms and not something else. So you have all this kind of messaging happening in your application to package the question that's being asked by the user and send it to this large language model with the right context. And by context, we mean prompts and sometimes information that is relevant. So if you have some external databases that are relevant to that question, you can say, well, this question pertains to this dictionary, for example. You need data from this dictionary in order to answer this question. And here are the type of prompts or the type of information you should send to this large language model. And then the large language model is able to utilize that information and give you an answer. Okay, but don't worry too much about, all these components you see on the slide here. But that's the basic idea. So before I go to this slide, let me show you briefly this tool. 1 minute. And then you can ask me questions. I mean, it would be nice to hear. Okay, let me share my screen. So yeah, this is our tool. And at the moment, we only look at Malawi, but we wanted to extend this to other type of disease surveillance in other countries. So the interface is fairly simple. And we have on the right all the fields of the form. So, you know, we have the fields that the form has available for completion, things like reporting facility, reporting district, the type of the case. And we also have some information about these fields. I mean, the main reason this was built was because a lot of community health workers who were using these forms did not have a guide to go with the form. So the form didn't have any, you know, appendix or addendum that was telling them, okay, how to fill in this field and so on. So we wanted to give information about, you know, what they were seeing on the form, and also the rationale, you know, why should you collect this data? What's the relevance of that data? What's the meaning of maybe options that there are on the form? So like OPD, what's the meaning of OPD and so on, abbreviations basically. And the other thing we wanted the users to be able to do is to ask questions. And these questions were questions about, you know, the data collection that they were undertaking. Now, in this case, it was disease surveillance. So they needed access to things like how to fill in, you know, this particular form. What is the case definition for a particular disease, for example? But sometimes there were questions like guidelines, you know, are there guidelines available, you know, where to find them, you know, what do certain abbreviations mean, and so on. Maybe I can choose a different field like phone number, reporting phone numbers. You know, how to document calls that you make for follow-up. So this was in the COVID-19. So these forms were also used for contact tracing and so on. So what we did in our work, we formulated some frequently asked questions that were relevant to what these healthcare workers were doing. And some of these questions had answers already that were formulated. So maybe to give you this example here, what are these abbreviations? So in this case, if the question is in our database, the answer comes straight from our database because it's already been checked. The answer has been checked. It's an FAQ. It's a frequently asked question. So this is to speed up also the access to this tool, right? So we have these FAQs and they have answers already. But the user should be able to freely ask other questions about diseases. So we have 3 databases that we worked on. One is case definitions. So these are things like, what are the symptoms for a particular disease, I don't know, cholera, and so on. Then we have these form and fields. So these are questions about how to fill in the form. And then we have a general type of questions about processes and so on. While this one, so this is now going straight to GPTs. Depending on the internet, it might take a bit of time to give us an answer. Now, what we wanted is that these answers are consistent with the national guidelines rather than something that comes from other sources. So this is where that concept of fine-tuning, yeah, or directing the attention of the large language model came in. That we had to direct the attention to specific documents rather than unknown sources. And the other thing that our tool has is a history of the questions that that person is asking. So that can be this can be reviewed offline or later on by the person. So basically, this tool that I'm showing you now it was leveraging large language models to achieve this interaction, this questions and answers interaction between healthcare workers and the knowledge. So in our case, the knowledge were the guidelines by the ministry that were formulated, some health dictionary, because there were questions about the meaning of specific diseases and so on. So a database of case definitions and also guidelines. Now, this is not fully complete, this tool, but is something that we are testing live with users to see whether it's useful or not. And I wanted to show you as an example of how you could leverage, generative AI for text for a particular application. So I'm going to go back to my presentation. Just 1 second. And I want to talk about key challenges. So what we've learned, right? So maybe before I continue, I should say that we did 2 things. One was to use a language model and tune it or fine tune it. And the other to try to build our own model. But there are some challenges, and I want to tell you about those challenges. So one is the data itself. Coming back to that idea of responsible and explainable AI, you need to have very good data. What if there are issues in the data itself, like they're intrinsic to the data, the way it was collected? So maybe it's insufficient, it's outdated, there's biases, and it's not transparent. You don't know where it's coming from. So we have to deal with issues like that. One is representation. So again, same issue as I mentioned before. Every time you use any computer system, you lose how much you've lost, right? Because that information loss can be important to the behavior of the tool that you are using. And sometimes there's an inability to capture the true context that you want in a computer program. I mean, this is where the skill of the expert and the programmer meet, because they have to talk to each other. The programmer needs to learn from the expert how to capture that context that's tricky. Just give me 1 minute, 1 second. Sorry, I'm actually having this session in my office at the university, and sometimes there's a lot of noise in the corridors. Apologies. And the other question is how to maintain and update the data. So I actually think that sometimes when we develop tools like this, we focus a lot on the actual doing, like, developing, coming up with the interface. And we are not as concerned as we should be with, what happens to that data, right? I mean, that's really important. That's what I would say. And not only the data that you have now, but then, how is that data going to maintain? Knowledge is never static. Knowledge grows, knowledge improves. And knowledge can contradict each other, right? You have new results that might contradict results that were in the past. How do these, knowledge-based systems, because these are very much knowledge-based systems, behave in that sort of situation? So big challenges when it comes to knowledge. Algorithms related. So these are challenges to do with the algorithms, and you've seen some of them, right? I mean, there's a trade-off between efficiency and accuracy, whether you use a black box model or not. But there's another thing, it's difficult to test them. Now, think about the tool that I've just showed you that we've built, right? How do we test it? I mean, how do we know how this language model that we fine-tune behaves? Are we able to 100% say that it's safe? You know, is it going to behave like properly? Is it going to give accurate information? Now, you would be thinking, well, how do you test a computer program? Well, most of the time, computer programs are numerical. So you test them with functions. You have a function that tests the input, the characteristics of the input, and you have some kind of function that tests your output. You know, you already have, you know, the accuracy that you're expecting, you know how to test. But with knowledge-based systems, you test against knowledge. So this really, really means that you have to have suitable benchmarks. They have to exist. You need to be able to test against something that's known, and that is hard. So this is where all sorts of theories are being developed to help with that. And one of them is this idea of human in the loop. So the human is always in the loop in the sense that it gives feedback, right? And I mean, this is not necessarily that foreign. It's not a foreign concept, because even with that spam email example we gave, you know, humans are in the loop because you help the tool. You are asked the question, is this spam? And sometimes you move emails out of the spam folder into the inbox. So, you know, by doing that, you're actually telling the model that this is not spam. You're helping train, you're helping to classify. So you're giving feedback, and the tool should be able to then improve its prediction based on feedback. And then here, limitations are being communicated and understood by the user. So that's important because every tool that's available out there can be misused. So it's important not to hide the limitations that are there in order for the use of the tool to be safe. And humans are important. And the other one is security and privacy. So remember, one of the example I gave of that LLM from Google, it was, you know, the clinical birth, it was using electronic health records. So again, issues of privacy and sensitive data. They have to be removed from the training data. Otherwise, you can disclose confidential information, and you don't want to do that. The other thing is that there is a danger of malicious interference. You know, somebody can tamper with. I mean, this happens with any computer system, but it happens also with LLMs. But we need to understand what kind of attacks are possible and how we can mitigate them. So yeah, this really means that for developing something like this, there has to be a good flow of expertise and knowledge between, you know, people who are programmers, people who are experts in their domain and understand what is happening and understand the knowledge and issues in the data and, you know, other things. It's not something that is magic, right? It just takes a lot of work and a lot of engagement. So that's what I've learned from what we did. So I'm going to stop here. I know this is not this is not making you an expert in generative AI. I mean, I don't think I'm an expert myself. I'm learning, but I hope it gives you a feel of the kind of application that can be built. So I'm going to stop here to take questions and feedback. because this is what I prepared for you. This concludes the content that I prepared for you. And there were some questions about contacts. So I've put my contacts on this slide, and you can contact me by email, preferable. Thank you very much.
Thank you, Amelia. So if anyone has a question, you can unmute and ask.
I mean, it doesn't have to be a question if it's a comment or something you thought about as we were going through this course. Yeah, feel free.
Hi.
Hello.
Thank you for the good job that you've done, but I have another question. Techniques around ensemble algorithms like the Bayesian and boosting, but I think you must have failed to, or rather forgot to talk about the bias variance trade-off.
I couldn't hear that. Sorry, you were breaking. Could you repeat?
I think you did forget to talk about bias and variance trade-off.
Okay. Yeah, I mean, I think I didn't cover many things. I mean, this was supposed to be 6 hours. But actually we did more than 6 hours, and even then we didn't manage to cover everything. I accept that. Maybe if APHRC wants to organize other courses, or maybe I can try to organize other courses, I can invite people and we can learn together and cover them together. Hello?
I can see there's one question in the chat as well.
Okay. TensorFlow decision forests. I have, but yeah, why? So I have used TensorFlow before. In fact, some of the things I did were using Python. So you can maybe write to me an email about the kind of applications you have in mind. Florence, I think that's the message from Florence.
Okay, feel free. If at all you have any other question.
Okay,
Mhm.
Which one?
No. I'm telling the audience, if at all they have any other question, they can unmute and ask. So far, I think you've answered all the questions on the chat.
Hello.
Yes, I
Hello.
can. Okay.
Yes, this is the time. Now, mine is not a question, but is regarding use of real health, mental health data. Because we have used some examples for the model, but I think we have some health data that mental health data that could also be used think it will be more good. The models are good, but we need to be more practical on the usage and
Yes.
interpretation.
Yes.
Yeah.
Yes, I agree. I mean, you see, like, I think in terms of mental health, I mean, I'm not, as I said, I'm not an expert in that area, but a lot of the data is collected in communities, right? Through surveys. And of course, you know, that can show maybe higher prevalence of specific conditions and so on. But, you know, what's the implication of that? I think it really boils down to the research and the problem they are trying to solve, and them understanding the limitations, not just of the models, but what that data shows. Yeah. So yeah, thanks for that observation.
Hello.
Hello.
Yeah, I just wanted to make it's a comment. I think for this great data to be managed well, we need to come up with the tools. And these tools, I think they would help each and everyone as we are collecting the data in the community. We should be able to understand the type of the tools being used. And when those tools are used, we'll be able not to come down, be able to analyze using the vector method, which has been explained, and other tools. But what type of tools do we have as under mental health unity? As we all know that mental health is the most neglected unit or department in all other countries. But for us to get, if you look at the tools which are being used to report data, for example, under the health sector, etc., and so on, they mostly talk about the neuropsychology, neurosis, etc., and other things. But other ailments are not really reported. For example, if you talk about alcohol and drug, anxiety, depression, stress, all those are related to mental health issues under non-communicable and communicable diseases. They are not coming out to be reported. But if these tools can be well organized and well articulated, we'll be able to capture a lot of mental health related issues. There is a tool which I was reading under WHO where they are talking about integrating TB and mental health. What are the things which might affect the client who is on TB treatment? Mental is pure burden.
Yes.
Then there's also stigmatization, isolation, neglection. So all those we need to come out issues which might affect a TB patient. We come and talk about mental health related to HIV. What is it that people they are not failing? They are failing treatment. Is it that the treatment is failing them? Is it the body failing them? Why is it all these issues are coming out? So when we prepare the tool, it will really help us to read what is it that is making these people not live a healthy life while they are on treatment. So we need to look to deeper dive to look into what types of tools we need to have at the community level, at I would say at the primary care. We go to clinical facility level, secondary, and up to tertiary hospitals. These would help us to analyze. Yes, we can understand the results which might come out from the labs, etc., and so on. But the tool to capture those information from the ground level, we don't have. So we need to look at first what is our stepping stone, where we should start off so that we can get those results using the vector tools I submit.
This was really great comment. I think it may help me picture, because like you say, you know, a lot of the medication does, it also made me think, you know, a lot of the medication does have an impact on the, psychology or the mental state of an individual. And some medications can be very powerful, right? And can affect the mood of the person. But that's not something you always capture in the lab result, right? Like you said, you need to use complementary data, and context is important to how you're interpreting those results and those numbers. So, yeah, I could relate to what you were describing from what I've been reading. So really interesting. And I really like what you said there about the dialogue, right? That dialogue has to exist between people who can, who are experts in their field, so mental health, clinical field, and people who are conversant with building these models. And it's a lot of experimentation that goes in, and looking at the data, analyzing, trying different models, validating the results that come, and so on. And, sometimes you look at the code and it's so small. I mean, maybe let me share the screen just 1 second. Just give me, this is a data set that I understand was discussed during these sessions. I don't know if I'm wrong or not. So this was a paper, a study that looked at the mental health and well-being of Kenyan adolescents. And this study has all the data that was used and the models available. So, people could replicate the results. I mean, maybe if we had time, I mean, we could look into replicating some of this and trying to break down these models. What do they mean? How does the data looks like, and so on. And the good thing is the paper is available. And I mean, when I looked at this paper, I thought, wow, I was overwhelmed, right? Because I mean, there's so many different questionnaires, measures that are being used, and all of this becomes numbers into your system that you're trying to analyze. And the good thing is that, this paper comes with all that data and with the R code. And, if you look at this R code now, after we have done a bit of R and a bit of modeling, you look there and you see it's actually not a very long code. I mean, look at it, it's not a lot. And then out of these come all of these predictions. But of course, the value of this is not necessarily in just writing these lines of code, is in understanding the variables and how your model behaves, right? And how your model performs. So maybe now what you could do, I mean, my session is finished, but maybe what you could do is to take this paper and try to make sense of how the machine learning models have been used in connection with this data that was used in this paper. All right, so there's a question.
Thank you.
Sorry.
Thank you. Yeah, you looked when I looked at the same paper you displayed, it is showing the correlation. I looked at the first presentation where you are talking about we want to measure the hypothesis. See that is in the negative or it is in the positive, isn't it? Where I've got the power of -1 and a 0 and +1. So look at the correlation. The GAD question where there is generalized and anxiety disorder. How did you measure that? It shows again to the results which have come out from the lab. When you take this client, we need to generalize. So looking at these questionnaire tools which we have, talking about GAD, etc., CAD, etc., and so on, those will be able to articulate and give us the results. And out of those results and the questionnaires which you have asked from the community, we are looking at mental health in the community. It will be able to give us a correct result and be able to analyze using the results which are coming from the lab. I like the same presentation you showed. Thank you.
Yes, and I want to show you something because I've been looking at this. So this document, let me just go to this document. I think I referred to it in one of my slides, was looking at decision trees to diagnose mental disorders. Now, these trees that are numerical, I mean, they live in the realm of numbers, right? But the interpretation is in the clinical tree, basically, because you will be looking at your patients according to the best practice, right, that's available. So you have the two worlds, right, the number worlds and the models that you are simulating, and the clinical thing. And I think that a good thing is for us to recognize that both of them are important, and you can never translate the real world into numbers. I mean, we haven't found a solution yet. It's an approximation, but it's useful, like you said. Okay, sorry, let me go on to other questions. There are some hands raised, sorry. Adeyinka.
Hello, thank you. In response to what Kennedy just, the comment he made, I think the solution to that has been found by WHO. There is this instrument, WHO MHGAP guideline for common mental disorders. It's to be used by non-clinician, non-specialists, non-mental health specialists. It can be used by you and I. It can be used by primary health workers. It's a guideline. It was made in 2010. It has an app now. There's an app. So the symptoms, it's like a questionnaire, but it has a description of symptoms that you ask the patient. Do you have this? Do you have that? Even to prescription of drugs, even to referral, when to refer, how to refer, the algorithm is there. MHGAP, I will write it in, you can download the app.
Okay.
So that's the solution, that's the clinical tool that is available for the primary health workers.
Okay.
Yes, I support that too, but looking at, I'm talking to the perspective of public health. We want to live, each and everyone to live a mental healthy life, okay? So what do? We start with the information at primary care, which is the primordial, where we need to give the information in the community. Now, we are working with the community-based volunteers or the neighborhood health committees who are in the community, in the zones, in the wards, etc., and so on. So how do these people going to give the information? And if they give out the information, how are we going to know when that client is referred from the community to the facility where the clinicians, the doctors, and etc., and so on, who are seeing those clients, be able to know where to start from? Or this client has been referred from the community and has been referred to the facility. What did the community manage to do when they had in touch or with communication with that client in the community? So why I said the tool should be available. The tool which is there for 2010, and there's a new one, I think, which was just designed, I think it's 2019 latest. We look at those tools, they're only talking about clinical arm. They're not talking about the community arm. But mental health is at community level. So we need to design a tool which would cater for the community and the clinical, where now diagnosis, management, and other investigations can be done to health sound. I submit.
Well,
Sure.
Amelia, I talk.
Go ahead.
It's just the same with that. I know that we're looking at it from the perspective of like something like malaria, where you can take care of your malaria and I think those to see it. I think they will get to that, but where they've gotten to now, and because there's need for quality assurance. There's need for quality assurance. Mental health has been misunderstood for long in many cultures. And in many cultures, we have a way how we take care of mental health beside the orthodox. We have an indigenous way of taking care of mental health. So as to put control measure, not to have a mixed up and confusion. For now, WHO, the level of care is still primary health, not community. What you're talking about, there are so many things to be put in place apart from the tool and the management guide. They need control, they need for quality assurance, and so many things, which one person cannot do. So WHO will still go into that. They are addressing the gap little by little. But for now, what we have available, the tool is still clinical.
Yeah.
It's still clinical for now.
Yeah, it's interesting. You know, I was looking at, I was reading an article about, you know, data collection for mental health. And, you know, sometimes, like, you know, let's say a study among students or young people. And, you know, we know young people, I mean, I have teenagers, teenager children, right? And, you know, they go through so many changes, right? So if you ask them, you know, a question now about how they feel, they might say, yeah, I feel this way, but, you know, tomorrow is different. So, you know, sometimes also, I mean, it's a silly example, but, you know, in the community, you can go with a questionnaire, but yeah, I mean, the data that you collect could be useful or not. It depends how you do that study, right? So, yeah, when you talk about clinical observations, you know, you'd be saying, well, this person has to consistently display these particular things. But I mean, that's just one application where you would need the experts. And it's not just about, okay, anyone goes out there and collects this data. I mean, that's what I would say, because sometimes you can, yeah, the person who collects the data is essential. And, you know, I live in Malawi, and I would say that a lot of the data that is collected might be a bit useless when it comes to being analyzed, because the way it was collected compromises its utility. You know, you go with questionnaires in English, but you have to translate. Well, where do you leave the translation to? You know, to the person who collects the data or to the person who reads? What if the person doesn't read? And then, you know, what's happening in a lot of symptoms, like, you know, it's also language related, how you explain somebody a concept, and then how they answer it. And not only how they answer it, is how you record it, because you're ticking a box. You're not putting the answer that that person actually gives. But, you know, I mean, this is the real life. The real life is complex. And, you know, we try to solve a problem using the computers and using these models. They will never be perfect. And I would say that as long as we are honest and have that human in the loop element, right? When we build models like this and test them frequently and over time and so on, I would say that can then lead to a good outcome. But yeah, not like a solution that's, yeah, let me collect some data and here it is. And because you can hospitalize people unnecessarily, right? And, you know, I think there was a comment about medication. And I was reading an article recently. This was a lady in the UK who suffered some anxiety during COVID-19, and the doctor she went to put her on these antidepressants because they said, oh, this is going to cure your anxiety. And you know what happened for her? Because, you know, we are individuals. We don't respond, you know, 100% in the same way to medication, right? In a kind of uniform way, right? So she developed extreme side effects to this medication to the extent that she was becoming suicidal. She had suicidal thoughts, but it was all induced by the medication. Now, in that case, in her case, it was shown that it was traced to the medication she was taking. Now, you know, I mean, so she was actually given the wrong treatment because the doctor did not know. The doctor who hospitalized her when she had an episode did not know the background of how she started to take this medication. So she was wrongly, you know, put into isolation and given more medication, but it didn't actually solve her problem. So, you know, let's say and coming back to the slide we had in terms of control, you know, here we come and we can actually build these algorithms. Yes, we can. They're there. You saw. I just pulled some R code and I ran them on some data. But where does the control lie? If the algorithm comes with an outcome, you know, yes, this person, you know, the responsibility relies on the human to use it and interpret it correctly and understand it and seek to understand it rather than blindly following, you know, maybe an outcome. And also, like it was mentioned by Kenneth, I think being able to discuss these algorithms and their limitations in a multidisciplinary team. You don't need to be an R expert to understand what could happen, you know, and when you use X model and Y model. So that's my kind of thinking from the work that I've been involved in and seen. Thank you so much for taking the time to come to these sessions. And I hope they have been useful. And oops, sorry. I hope they have been useful. And if you want to be in touch, you have my contacts, and hopefully we can meet maybe in other forums. Thank you very much.
Thank you
Yeah,
so much.
thanks.
Oh, sorry.
No, go ahead, Diana.
Okay, Sylvia. Okay, take it away.
Yeah, thanks so much, Amelia, and for staying for 3 days, going over AI and machine learning. I hope you've had, for the participants, I hope you've enjoyed the discussions. I think I've really had the questions you raised at the end, and I've listened to the discussion and questions you raised at the beginning. I may have been on and off at some point, but it's good to see that we can put the clinical aspects, the data we collect to use in terms of informing whether it's outcomes or predictions around mental health and how that happens, especially in the realm of vector machines, or whether it's decision trees, in terms of using those, and what the challenges would be if you adapted or used those tools. So one thing that we really know is the data, I mean, the models are as good as the tools. So if your data or tools are not good, the models will not fix what has gone wrong. So we need to be very wary of how we collect the data, who is represented by the data you collect, and what do the predictions mean. And also, because we operate in some kind of sometimes a black box, we need this multidisciplinary team to bring the human aspects in the interpretation and in the improvement of the models. I really like the dialogue about the models and using real data. So you will have a chance, like we saw the study in Kenya shared their data. So So that's really good. So it helps us to understand. And one of the things that we promote is to have this open source and open resources for you to be able to use. So one of the things there that I really like with the paper is the fact that they could publish the code, they could share their data. So that's a good thing for you to be able to go there and play with the code that you have developed right now, but also thinking of what other data sets might tell you. So and also the challenges with community, when we're looking at community aspects of monitoring or generating information on mental health and how that aligns with the clinical aspects, the ones we see in primary healthcare in the clinics, and the value. I think the issue about the fact that, yeah, we have so many, we might have cross-sectional studies, so we pick something from the different tools based on one instance, meeting an individual in one instance. We know that there is value in having the longitudinal data sets because they follow up people for a longer period of time. But yeah, maybe the longitudinal studies may be fewer in our context, given the cost of running longitudinal mental health studies, especially whether it's community or clinical. The cost still comes up as an issue, but we could leverage the tools that we have to improve the understanding of the data and the patients and how we could improve decisions around that. I want to reiterate again, Amelia, thanks so much for the 3 days, and thanks so much for engaging continuously with the participants and the follow-up questions. So if you have any questions, please feel free to reach out to Amelia, and we'll see how much interest is there for further involvement in other machine learning models and algorithms, maybe AI models and algorithms, and whether we can set up some extra sessions, but the videos and the materials will be shared from this course, and any extra resources will be available online. So thank you once again. Back to you. Thanks, Amelia. Thanks to our participants for holding on up to this day. So after Wednesday, we continue with the other sessions, 2 more sessions on this, and looking forward to see you then. Enjoy your evening or afternoon, and see you on Thursday. Back to you, Diana.
Thank you, Sylvia. I guess that's it also from me. Thank you so much, everyone, for joining this training session. I hope that you learned a lot from the meeting that you've had. So looking forward to meet again on Thursday. So have a lovely evening. Goodbye.
Thank you. Bye-bye.